So I don't have a real understanding of where I'll be in 5 lectures. So, I have sort of an understanding on what I will say today. So hopefully this will be an interactive process. After all, I'm doing it on the board. Of course, I have prepared a little bit. So El-Hanan said that this would be a boot camp. And boot camp are traditionally, I don't know, Israeli boot camp are probably much worse than Swedish boot camps in the first place. So, you ask the audience questions, and if they give you the wrong answer, they have to do push-ups, right? All of them. Okay? So I decided, that when you have an audience that's, not forced to go there, I decided to reverse things. So I ask the audience questions, and if they answer correctly, they get chocolates. Okay? So I've prepared now some Lindt chocolates here. So good answers are rewarded by chocolates. And also, when I completely lose one of the worst experiences as a lecturer is that you sort of at the end of a lecture suddenly get the question that you thought that everybody knew in the beginning, and you sort of explained in 30 seconds at the beginning. So these kind of stupid questions, please ask them. They'll also be rewarded with chocolates.
So you're not going to go dark chocolate?
That would have been the turn way to do it, so but
chocolate after a question, it means that it was a stupid question.
It was a question that brought the lecture forward. For one reason, why this is deemed so is up to me. Okay. Good. So please ask questions. Please tell me when I'm saying wrong things or when you can't see what I'm writing or whatever. Okay. So our generic constraint satisfaction problem is going to be 3-sat for a while. So we have, variables. Some are negated. And whenever I put numbers, I'll have, in fact, plus minus 1 notation, as in the... and in Boolean cases, minus 1 is true. Okay. And this is a known NP-complete problem, so it's hard to find the optimal assignment, right? We don't believe in polynomial time that we can find the best assignment. But we're going to talk about approximability, and then I'm going to talk about max 3-sat. By the way, I'll be very bad with motivation and references. Okay, so if you want to know where something comes from, you can ask me, and maybe I'll know. And motivation, I'll just think that this is great stuff, and you're going to think so also at the end of the lectures. And if you don't, that's your problem. Okay, so we have max 3-sat, and we want to satisfy as many as possible. And since it's hard to determine if you can satisfy them all, we won't be able to solve this perfectly. So what we'll be interested in is the approximation ratio. And this is, if we have some algorithm. I'll have some polynomial time algorithm in mind. And the ratio we'll be interested in is the minimum of how well the algorithm does over the optimum. Okay, that's the approximation ratio we get. And also I'll be dealing with something here which I'll call E3-sat. And this is simply that each clause is of length exactly 3. Okay. Thanks. So now I'll ask a first easy question, and mostly to the answer. Can anybody get an approximation ratios for max 3-sat?
Half.
How do you do it?
I take the all 1 assignment, I take the all 0 assignment, and one of them is going to satisfy more than half.
Okay. Since you're so good, that was not a word. You need to do better to get chocolates, okay? That's a good one, yes. What?
7 over 8.
7 over 8, yeah, why?
For if not all the variables are the same in the clause, then the expectation is 7/8.
Yes, you can do it in expectation. Can you do it deterministically?
Yes, in a linear of expectation method.
Okay, good. So 7/8, okay, by random assignment. And can be de-randomized. And so just to repeat this, if you pick these three guys randomly, the probability that they're all false is an 8, so on average you'll satisfy 7/8 of the clauses, and the optimum will never do more than all of them, right? So you get 7/8. So the first theorem So the theorem that I'm going to spend a good fraction, well, probably all of today and some of next time to try to prove is that it's NP hard to do better. You cannot beat 7/8 by more than, for any positive number you can't do better than 7/8 plus this number. Okay. And in fact, I've called such a thing approximation resistant. Well, I sort of by abuse of notation, I'll say that 3-sat is approximation resistant because you can't do better approximation than what you get by just don't look at the instance, flip random bits, and be happy. Right? That's how I'm gonna. So somehow 3-sat is an extremely difficult problem. Even if I give you something where you can satisfy all or almost all the clauses, then in fact it's hard to do better than what the random assignment does. Okay. How many have seen the proof of this theorem? Okay, that's a good fraction. How many could do the proof of this theorem right now? Well, that's if somebody raises their hand, I'll step down. What?
Do you mean the whole proof, like also including parallel repetition and everything?
Well, that's a good point. But yeah, so some of you might be bored, but I'll try to do a lot of the details of this thing. So it's going to be a very simple idea. So this have, say, M clauses. So the overall idea is extremely simple. We're just going to, in polynomial time, we get in a formula phi. We're going to produce a different formula, which assume it has M clauses, which has the property that if the original formula is satisfiable, so is the second one. And if the first one is not satisfiable, So this is, of course, of psi. Not only is the resulting formula not satisfiable, it's in fact extremely strongly non-satisfiable, that no assignment can do more than sort of this expected ratio 7/8 plus epsilon. Okay. So are you happy that this such a transformation will in fact prove this theorem? Because if, I don't know how many people, is one of these...
It's worth it to explain why this is enough.
Good. So Guy can explain why this is enough.
Me?
Yeah.
Yeah, so if I wanted to, if I could tell whether a formula is satisfiable, so if I know that, suppose I could tell between a satisfiable formula and one which is not even 7/8 plus epsilon satisfiable, then using this process I could distinguish between phi which is satisfiable and phi which is not satisfiable, even if it's almost satisfiable, because I would first apply this transformation and then I would apply this, whatever algorithm I have for psi to distinguish between the cases.
Good, thank you. So the one point I was supposed to bring up that I didn't. So there are a few things we should get. One we sort of touched on, but we should determine once and for all. First of all, these approximation algorithms, I sort of gave the ratio. We could ask for two things. Either they just determine the optimal value, say that this is the maximum value of the number of clauses that can be satisfied, or I can actually ask to get an assignment that does this. Okay. Clearly, it's harder to find. It might be harder to find a good assignment than actually determine the value. Okay. So I won't be very explicit on these things, but one thing to observe here first: this argument that the guy just gave. Do we need to find the assignment, or is it enough to just to determine the value approximately?
So I think it's not to only approximate it, but then you have to add some constraints. For example, the algorithm is forbidden to return any value that is higher than naught. You're not allowed to overestimate.
Yes, yes, yeah.
Other than it's fine.
Yeah, yeah, yeah. So you need some external guarantee that it doesn't. Yeah, if you don't have a good proof, you could think of all crazy.
One, right, and then my approximation ratio as it's written there is 1.
Yeah. Okay. Good, good. So yeah, we'll assume that the algorithm. So we need to add the constraint. Always. That's a correct. That's. But it's enough, in fact, to approximate the value. That's all I need to determine if this original formula is satisfiable, right? So it turns out that almost all hardness result is what I'll prove. Mostly, it's enough to find, to know the value. While in fact, most approximation algorithms that I will not do, in fact, they do find a good assignment. So somehow you get the best of these things. When you have an algorithm, you actually do the harder thing, and the hardness result just requires you to do the easier thing. But I will, in general, allow a randomized algorithm, and then I will, in fact, have the expectation here. But then you should remember that I will only allow randomization over the internal choices of the algorithm. I won't have any average case instances here. There are worst case instances, but randomized algorithms. Good. So in fact, once you know that such a transformation exists, I will actually deliver on this eventually. There might be a completely combinatorial way to do this. If you gave it to somebody in the 80s, say, please do this. It's not. Maybe you guys already have some ideas how to do this. So when you space out and stop listening to me, you can just think of other ways to do this. So I want to talk, lots of the intuition and lots of the results will be from verifiers that verify proofs. And satisfiability, the first time you teach satisfiability, you say, well, this can be efficiently verified. If you have a three-set formula, phi or psi here, you can write down a satisfying assignment, and then you can just verify it. You go over all the clauses and just check it. Okay. And the point now is that they look to be about the same in this, but we all know how we verify proofs. I don't know how you verify proofs, but if you get the proof, it's sort of, at first attempt, you don't read it all and check all the details, but you sort of look at an interesting point and check that checks out, right? And this is exactly what we'll do here. So I'm sure if you were given by hand a formula with 100 variables and 3,000 clauses, you wouldn't go through them all, but you would say, write down a satisfying assignment and then just check a random clause. Right? And normally that doesn't work too well, because there could be an assignment that satisfies all the clauses except one, but note that that's an extremely good proof for psi already in a formal way. This is sort of an important point, so let's see if I ever... the claim I'm sort of making, let's think of it as the claim that the original formula phi is satisfiable. Okay? And we sort of think as you as extremely lazy verifiers, so you're not willing to read very much. So in fact, you only want to read 3 bits. Which sort of corresponds to a clause and sort of picking a random clause and checking it. So my point is now that it's much better to read a random clause from psi than to read one from phi. Because if you read something random from phi, you don't have any really guarantees. But if you read a random clause from psi, you in fact have almost an 8th probability of catching somebody who's lying. Right? Because we know if the original form was not satisfiable, any assignment will falsify almost an eighth of the clauses. So you can be very efficient. So this is really a remarkable statement, right? So this is saying that, you know, you can check, you have a formula phi with 1,000,000 variables, and then you translate it efficiently to psi, and then you can check it by just reading 3 bits. Okay. All right, everybody happy with this? So yeah, so I'll do the. So what the thing will need, so the claim is that what we're about to construct implies incredibly efficient proof system, and we'll actually need to start with a very efficient proof system, and that will be the Pcp theorem by Aurora, Lund, Mutwani, Sudan, and Segeti. So the Pcp theorem says that you can take any, you know, 3 such formula, or any NP statement for that is, and have a polynomial sized proof that's checked by verifier that flips order log and random coins, reads only a constant number of bits, and rejects any proof for an incorrect statement with a probability that's independent on the size of the proof. How many people saw the Pcp theorem before? How many did not see it? That's okay, so you will almost all have seen it, and you sort of believe it and see it's a fantastic theorem, right? How many agree that this is, apart from this constant 7/8, agree that this is more or less that these two statements are essentially the same? Who needs to be convinced of this? Nobody needs to. Good.
Well, you can just.
We can. You should be prepared, you know.
I wasn't expecting that.
What?
I wasn't expecting that.
You can just change the formulation so it will be that. Like you can state that the Pcp theorem is the existence of a reduction for which satisfies this only with slightly different bound.
Yeah, but let me. But let me still. Yeah, so you can say that you can redefine the Pcp theorem to say this with a different constant here, right? But then you're sort of cheating, right? Because then you've already established what I'm going to do now on this board. But there's a pedagogical point also. I don't know how to pronounce. Okay. So the person that we constantly have in mind when we're talking about this is the unscrupulous prover. So what does the unscrupulous prover want? Well, he just wants to convince the verifier. He doesn't care if a formula is satisfiable. He just wants to maximize the probability that the verifier accepts. He doesn't even look at the formula. He just knows what the verifier is going to do and just try to make the verifier happy, as some students do, right? They don't do their homework, they just want to convince their professors. Like also some researchers do. They just want to please the referees and they don't care if their theorems are true. So what's the problem? What problem does the unscrupulous prover face? Okay. Well, he sort of looks at the verifier, whatever this might be in the Pcp theorem, and then it's sort of the verifier would have some random coins. So if the verifier just have zeros as random coins, the verifier will do something. Suppose, just to make life a little bit simpler, that this, let's pretend that this number is 3, to make it look even a little bit more. So he knows that if the verifier's random coins are all zeros, then in fact he's going to look at bit 17, bit 23, and bit 48 of the proof and check that they're not all -1. Why he does this is beyond him, but that's what he can read out of the verifier's program. After all, the verifier is just a program, right? Well, if the verifier's coins are 0, 0, 0, 1, he'll read some other bits. Bit 18, bit 27, not just how bad random number generator I am. And then he'll check that they're not all ones. And finally, when the verifier coins are all ones, he'll read some other 3 bits. But if you just try to tell what's going on, well, what this does is sort of, we'll think of these bits of the proof as variables, and he'll just write down his condition saying that, well, it may be that one of these 3 bits are false. Remember that -1 is true. And he'll write down that, I don't know what this is, but never mind.
The other way around.
Pardon?
Is it the other way around? Right? Not all -1.
Not all -1 means that they shouldn't all be true, which means at least one of them should be false. I think I got it right. But it's the principle that matters anyhow.
Up to a sign.
Yeah. And the point is that, if the... But Christos,
Yeah.
right? Whatever this is.
I had my signs in it.
Yeah. But so then the next step up is to say, well, suppose he doesn't have such a simple... And now you see that if this is the case, I mean, if conditions are like this, I exactly have a 3-sat formula, right? This is the first clause. This is the first clause. The probability that the verifier accepts under a particular proof, which is just an assignment to all the bits, is exactly... So we're trying to optimize this thing. Yeah. And the next thing to say is, well, it might not be such a nice that it's a clause. Maybe this is another formula of a 3NF formula, but then you just put the formula there and take the conjunction. If it reads more than 3 bits, you take a little bit and then you have to apply a transformation. But it's really, if you think about the unscrupulous prover and how he convinces the verifier, it's really writing down all these formulas. That's reasonably okay?
How do you get a 7/8?
No, you don't. You don't get 7/8, okay? So this is here you get some constant that depends on CA, where CA is this number, right? So now to get the 7/8, we have to start doing work. That's true. Yeah. But this is where we're going. And this I won't prove. This is a long and complicated proof, and I'll assume that this theorem is proved. There was an original proof by these guys, and there's a new proof by Denor. And this is highly recommended if you want to read, but will take me a couple of lectures just to prove this. I won't prove this. Okay? Nothing, did you?
No, I'm just wondering, since you said this, how long does it take? If you really have a good audience, how many hours would it take?
So this itself is a culmination of many works that
No, no,
came
I know, I
before
know.
that. And it's
No, I know, but in the present technology.
In the present
we spoke
technology
about
from
this
scratch?
in Jerusalem for a semester when this just came, so.
Yeah, so it doesn't take a semester. I mean, Irit's proof is probably simpler.
Yeah,
Two
yeah,
lectures?
Proof is like probably 4 meetings of 2 hours each if you do all the things.
10 hours.
Probably less. It's a good audience.
Well, it depends on who the students and it depends on the speaker.
Yeah. Good. So let's. So this thing we get so far from the Pcp theorem is nearly what we want. You know, by searching things, this is a 3-set formula. This is a 3-set formula. And it has this property that we preserve satisfiability. And then the best assignments, we get some ratio CA, where this is just a constant smaller than 7/8. And the first proof will really give a constant here that's extremely close to 1. Okay. So the name of the game now is to improve this constant. So the next thing I want to do is to make a 2-prover game. So the 2-prover game I want is that we start with this, this end result of the Pcp theorem, and the verifier will pick a random clause and look at this and a random variable from this. Well, there might be, there might be negations here of some of the guys. So he sends the identity of the clause to P1, he sends the identity of a variable to P2, and then he gets values for all the three variables in the clause from P1, and from one of the values of P2, and what he wants to check is that Cj is satisfied and Xi consistent. So notice he gets values for all the three variables in the clause and two values for one of the variables, and he checks that those agree. You're happy with this? So what's the optimal strategy? So if the formula is satisfiable, there's a strategy for P1 and P2 that always makes the verifier accept, right? They just agree on a satisfying assignment and they tell the verifier this. What's the optimal strategy if you can only satisfy a fraction Ca of the clauses? How well can they convince the verifier?
So they do the obvious. They select a maximally satisfiable thing and they give that.
Yeah, that's the intuitive thing. Is that the best they can do?
They could do random, of course.
Yeah, that's a good question. They can be random, of course. Does it pay for P1 and P2 to be random?
No.
Why not?
There's an optimization problem.
Yeah, there's always an optimal deterministic strategy in these games. Everything is known. The formula is known. The verifier strategy is known. So if you're new to this, let's fix any possibly probabilistic strategy for P1, and then say, when he gets a clause, when P2 gets a variable, he can sort of see which clauses goes with this one, and he picked the deterministically best strategy for himself. So you can make him deterministic, and it's easy to see that then you can make P1 deterministic. So what's the best strategy? Well, once P2 is deterministic, he's just an assignment, right? And once you fix P2 to an assignment, we can look at P1 and says, well, whenever the assignment of P2 satisfies Cj, we'll just answer according to it. And when it doesn't, we'll flip one of the variables. So except in the very few cases when when the assignment doesn't satisfy the clause, what happens with probability Ca, they'll always win, and when it doesn't, they'll lose with the probability a third, because the checking question will actually agree with where P2 cheated. Okay? Everybody happy with this?
Can you repeat that?
Pardon?
Can you repeat that?
Yes, so were you okay with the deterministic P1 and P2? So P2 gets an assignment, right? That he turns into an assignment because he just gets identity of a variable and he returns the value. So whenever and most of the time, that assignment will they fix this to be the best assignment, which will satisfy a fraction Ca of the clauses. So whenever the clause is satisfied, P1 will answer accordingly and they will always win. But when it doesn't satisfy the clause, P1 will cheat on one of the three variables and they'll be caught with a probability 1/3. Okay? Thanks. So when I did the bad explanations,
Shouldn't we be throwing stuff at you?
Well, you can bring food. There's a lecture tomorrow. You know, you weren't prepared for this.
You have to prepare. That's what you say.
Yeah, I might do it for time for it. Good. So it's good. We made in a two-prover game. We moved a little bit closer to one, and not too much, but a little bit, which is not good. And now comes the second great statement I need. So what's the k-parallel game? Well, we just have the standard game. We now just repeat it k times. So we pick, the verifier picks k clauses. He picks one random variable in each clause. He sends the clauses to one guy and the variables to the other. And then he gets back assignments, and he just wants to see that the assignments are satisfying, they satisfy all the clauses, and they're consistent. You know, it gets the same value for all of these things. And what you might hope, if you haven't seen it before, is that the optimal strategy for P1 and P2 would sort of go down as exponentially with the number of repetitions. After all, we have to k games. So unfortunately, two-prover games are fairly complicated. So it doesn't go down with this exponent, as Ran Ras proved a long time ago. It does go down exponentially with k, but possibly with a different exponent. And this is the parallel repetition theorem. And the proof of this was originally very complicated and in a horrible sorry, Ran. It wasn't a lot of fun to read, but it was a great progress, and it was open for a number of years to prove the parallel repetition theorem. The proof has gotten simpler and the constants have gotten better, but also proving this parallel repetition theorem would be, I don't know, 2 lectures these days. So it's a general statement about parallel repetition of two-prover games. You know, the exponent goes down, the acceptance goes down with the number of copies, goes down exponentially, but the constant might surprise you. Any questions about two-prover games and how I came to this conclusion? No? So now I want to have an abstract game which I'll call label cover, which will have two kinds of vertices, one to the left and one to the right. It will have some edges. For each edge I will have a projection. And the solution to this label cover is to label each vertex. And for the guys to the left, I'll have a small label. And for the guys to the right, I'll have, which will be from a set, capital S in size. The labels to the right will have a label from a set L, which is the large. And the way to check such a label cover instance is that, you pick a random edge, read the two labels, and look at the corresponding projection and see if the projection is correct. So now I see if I can move too quickly. So what does this have to do with the two-prover games? Yes?
It is a two-prover game.
Yeah. Good. You want the chocolate? Yeah? You want to elaborate?
That's it.
We can take this. So from this parallel repetition, we can draw an instance of label cover.
Yeah, so these guys to the left are, tuples of variables, right? It's a sort of a question with a tuple of variables. The things to the right, maybe I should have this chocolate back,
Okay, so the labels on the right side are assignments to k tuples.
Yeah.
Like S would be 2 to the k.
Yes, S.
And L would be h to the k.
Yeah, or possibly 7 to the k.
Yeah, I mean, yeah.
Because I didn't discuss this, but somehow P1 should always return things that are accepted by. It doesn't make sense for him to return things that don't satisfy the clause, right?
Right. Oh, and it's a projection, so for everything you must. Yeah. Okay.
Yeah, and the point is that these projections are just checking that we have this. You're happy with this? The things. These are assignment to variables and clauses. And to variables and clauses. These are assignment to k variables, as in k clauses, and these projections are, take take coordinates sent to the other guy. Right?
I wouldn't say they are assignments, I would say they are the names of the clauses. The names of the
Yeah. Fine. Yeah.
variables.
Yes. Sorry. Yeah. So they're the names, and the labels are the assignments.
The labels are this.
Yeah, you're right. Thanks. So in fact, if we're abstracting it away, it says, if the original formula we started with a long time ago, namely this formula, if this was satisfiable, well, then we had something, then also this was satisfiable, then we had perfect completeness in the basic two-prover game, then we had perfect completeness in the repeated two-prover game, and that gives a labeling that satisfies all the edges, right? On the other hand, if we started with something that was not satisfiable, then we did CA there for pi, and then in the parallel repetition, this went down with like exponential in k. And if we just change parameters here on just slightly, this means that the best labeling, which is a strategy for the two provers, will only satisfy a fraction epsilon of the two, if we pick k large enough. And in fact, the sets of the labels will grow with epsilon, but only polynomially large, right? This was like, c prime to the k, and these were other things to the k, so they're exponential in epsilon to start with. So claim now it's a corollary, it's NP hard to distinguish label cover instances where you can satisfy all the constraints, and label cover instance where you can only satisfy an epsilon fraction of the constraints. And this just follows by this, unscrupulous prover sort of argument. I mean, the unscrupulous prover that tries to convince a verifier sort of tries to satisfy as many as possible. And if he can figure out the optimal ratio, then in fact he can distinguish these two cases, and he can determine if the original formula phi was satisfiable or not. Okay? So do you get this for non-constant epsilon? I'm saying for any constant epsilon here. I'm not asking if it's true for non-constant epsilon. I'm just saying that, does this proof work for non-constant epsilon?
The alphabet size would depend on epsilon here, right?
Yes, the alphabet size depends on epsilon as inversely polynomial in epsilon.
So the instance also grows. So the instance becomes super polynomial if you make epsilon subconstant.
Yeah, so the problem is if epsilon is subconstant and k is super constant, and the number of things here is like m to the k, right? Because we have, and this side is like m to the k. And n and m are polynomial. So if we want this to be a polynomial time reduction, we want these numbers to be polynomial, and that's why we can only do this for constants k. But we can return this. It turns out that you can actually get non-constant k's, non-constant epsilon, but then you have to redo everything, and you can't just rely on parallel repetition, and this I'm not going to do. So thank you. Good, but now we're starting to close in on our we've made progress, right? We now have made progress that in fact we're in a situation where it's sort of, we should think of these labelings as proofs. And the property is when we're trying to prove true statements, all checks will work out. And when the unscrupulous prover is trying to prove false statement, it can only satisfy very few of the constraints, right? That's why we're in such a good situation. But the problem is that these labels are big and we'll have to make them smaller again. You guys want a break, by the way? I usually just talk for 45 minutes, but now I already talk for an hour, but I'll try to talk for another. So now let's see what we're going to do. So the thing all of the thing we've done so far is we're going to remember this label cover. We're going to remember that it's hard to distinguish the case when we can satisfy all the vertices, satisfy all the edges, and we can only satisfy a very small fraction. And now we want sort of to build on this. Maybe we'll fact. So this is the theorem I promised you. I don't think I'll get to that today, but I'll start proving this theorem and we'll see how far we get. And I have to define the problems involved. So max 3 lin will be the system of equations where monomials of degree 3 is equal to constants. Why do I call such a nonlinear system max 3 lin?
Just switch the basis and it's linear.
Yeah, yes, you say it a little bit more loud.
Sorry, just switch the basis and it's linear.
Yeah, this is just parity questions, right? So that's why it's a linear. It's just, so if you can satisfy all equations of this type, what happens then?
It's linear algebra.
Right? Then it's just these are linear equations like this, and there are bits and you 0 ones and you add them and it's linear algebra and you solve them in polynomial time. Okay. So if you have m equations here, Oh. Well, now I give this away, but so if you do, so how do you, well, can you do this if you want to? Now I sort of, you should be able to do a half, right? So what's the easy argument you can do a half here? Any?
Just try all zeros or all one.
That works. That's, or another way to do it. All zeros and all ones, yeah, or just a random one also works. But all zeros and all ones, but that's not as, and then a random one, and does equally well, so. So the question, can you do better? So, what we're really trying to prove again is that this predicate is also approximation resistant. That you can't do better. I mean, from an approximation ratio point of view, you can't do better than picking a random assignment. That's what we want to prove. And then we'll see how this implies what we have above. And then we're going to use an idea that was around for a while, and it's, we want to code sort of the labels. Right? It was a.
I'm just curious, how existentially, how bad can it be? What do you get? 1/2 plus 1 over root n? Just a system that.
How bad? So now you want sort of.
No, this is nothing to do with computation, just as a algebraic, combinatorial algebraic question.
Well, you can make the optimum exactly half, right? The way I set up things. You can just have two equations which are each other's negations. Without cheating, I can probably make it. Then you can take and with 3. Yeah, maybe you square it down then. Square it down. Yeah. So you can always worry, but now you always get, aggressive for more. How can you make this a function of n and m and so forth? Sorry, I got excited. So now we're going to code these assignments, and what I'm going to do is I'm going to use something called the long code, which was introduced by Begar, Goldrash, and Sudan, which plays an enormous role in this field. And it's one way to view it is that I'll have some label in some set, and I'll use exponentially many bits in this. And I'll think of these bits as a function. So it takes inputs which are -1 to this, and simply what a correct long code of the label lambda u should be that you return this coordinate. So it's a dictatorship function. So the way we're going to do this is that for each vertex here, which should really contain a label, we'll make it a truth table of a function, which should be the long, in a correct proof of a correct statement, it should be the long code of the corresponding label. Sometimes I call this the standard written proof because it was used so many times. So we want to replace it there by exponentially many bits, and it should be the long code of the corresponding label. In the correct proof of a correct statement, it should simply be the long code. We'll define the long code over there. Okay. And the name of the game now is to check this standard written proof by cleverly asking questions in it. Yeah. So always when you're looking at polynomial time reductions, you should always be wary of exponentials. So are we afraid of these exponentials? Are we afraid? Yeah, S and L are constants that depend on the outside L. So they're in practice, of course, we would never be able to represent these proofs with a number of atoms in the universe. But it's a constant, so we're happy. Okay. So the way we're going to do it now is to make cleverly checkable proofs is that we'll pick a random edge here, and then we have a little table sitting here, and a table sitting there. This will be my FU, this is my GW, and we're going to read some bits in them. So this, when I say random, I mean uniform and so forth. So I'll pick one random point here, which is x. I'll pick random point there, which is y. And then I'll cleverly construct this third point z which is sort of the product, which is actually the XOR of these two guys, almost all the time. Well, maybe let me. Okay. And then I'll check that the bit at the Z position is actually the product of the bit at the Y position and the X position. Is everybody happy with this? So now I'm just reading 3 bits, right? That's, we have constructed this huge object and now we're just reading 2 bits. So now I claim that if we in fact have a correct standard written proof, and which sort of implies, I'm sort of just repeating this, that we had the true statement to start with, we had the perfect strategy in the 2-prover game, we had the perfect strategy in the repeated 2-prover game, we correctly coded the labels, then in fact I claim that we accept this test is going to accept with probability 1 minus delta. Well, delta is exactly this number. So now we're just this is not a difficult statement, this is just trying to understand all the things we've put together. So some of you look a little bit tired, so well, who sees that this is true? That's too few. You have to do push-ups. I'm not going to give you chocolates for this one. Okay, so let's.
Johan, I always have to think like for half an hour if I have to pick 2 from the large and 1 from the small, or in the other way around. So how do you see that?
Well, so now you're asking the meta question. Why should you do like this? Why shouldn't you have 2 in the small and 1 in the big?
Yeah,
and
something like that. Like I always have to think a lot. Like
yeah, but we can talk about that tomorrow. I think we can talk about that tomorrow. Let's just check how these things are. Okay, so let's try to unravel this statement we just had. So what do I mean by a correct standard written proof? Well, at each point here sits a label, right? This guy has a label lambda u and this have a label lambda w. And we have the property that the projection, did I erase this? That the projection of lambda w is equal to lambda v, right? That's exactly what it says that we have. That's on the label cover level. The fact we have this label covering thing, we have the projections, and when we have these good labeling such that respecting these projections. Now that we have correct long codes of things, let's look at this very bit we're trying to read there. Well, we have this table FU. And if you have a correct long code of a correct thing, this should be the corresponding coordinate of x, given by this label, right? In the same way, the guys we're reading over here, the g's, we're reading the y and z points over here. Well, in a correctly coded thing, these guys will be the corresponding coordinates in the bigger table. Okay. And now we go back how these things were coded. Well, we see that the z variable we just defined to be the y, most of the time, with probably the 1 minus delta, it's the corresponding y variable times x at the projection. This is with probability 1 minus delta. And this is exactly so with probability 1 minus delta with the correct coding, we've just set up things so they're actually perfectly aligned. Okay. You're happy with this? And maybe we'll do it again just to punish you on the tomorrow. So let's call this L Z delta. Okay. So now the important soundness lemma that, well, we'll see what we're going to do, is that suppose we have, first we can say, well, this is just checking the identity. Did I even erase this? No. We're just checking whether 2 bits are equal, so we can only hope to have soundness like a half here. But I say that if we have a proof that makes the verifier of this protocol accept with a slightly more probability, then in fact we can extract a labeling that sort of satisfy a good fraction of the edges in the label cover. Okay. And if we have this lemma, that's the end of the proof of approx max 3 lin. Okay. I won't be a subtlist. But these are the claim is that now we're essentially done. Okay. So we need the completeness. The fact that we had a good proof that accepted with good probability was very simple. The soundness lemma will be moderately difficult. Once you have set up the machinery, it's not very difficult to prove, but we'll prove it next time, I think. So the only thing I want to do now is sort of, by a louder and louder voice, try to say that this finishes the proof. Okay? Does anybody want to explain what did we want to prove? What do I claim that we proved? Well, I cheated you on one detail. Yeah. Sorry. I cheated you on one detail. Does anybody can come up with a proof if you're sort of you didn't follow it all now? Okay. And you just want to make this stupid verifier accept. How do you make him accept?
Say one always.
Say one always. Oops, sorry.
Yeah, I wanted you to hit.
No, I was more worried about the person in front of you. Right, so you can say one always. You see this, if you always, if you complete all this table by ones, we're just checking that the one bit is equal to the product of two other bits. Okay? So we'll need try to be taller. So I'm not going to let when I use my long codes, I want to enforce the property that if you negate all the inputs, in fact, then the answers is negated, and this will be called folding. And the way I'm going to do it, is that for each pair x and minus x, I'll just store one bit in the table. And by convention, I'll say it's the first guy in the pair. And when I now want to read z, I have to look at its pair. And if it's the first in its pair, I'll use that bit. And if it's not the first in the pair, I'll use the negation of that bit. So I'll make sure that this sort of destroys this strategy of only putting ones, because all the second halves, when I ask things in the second half, you'll get the minus ones. So the thing I claim that I'm more or less giving you the best part of the proof of is that it's NP-hard to distinguish instances of max 3 lin where you can satisfy 1 minus delta fraction from the case where you can only satisfy half plus delta prime fraction. And why is this so? Right, so the way to think about this, I can't spell this. Right, if you think about the unscrupulous prover in these systems, when we've coded everything by the long code, and the unscrupulous prover is sort of thinking how to complete these tables, I claim what he's looking at is exactly a max 3 lin instance. Right? He wants to go over all the verifier coins, picking all these things, and knows that in the end the verifier is going to read 3 of these bits, and he's going to check an equation of these that via the folding might turn out that the product of these 3 bits should be 1, or the product of these 3 bits should be minus 1. Right? Now you're not nodding as you're supposed to. I can hold you here for another, well, not that many minutes, but still. Is it anybody who wants to understand this that still doesn't understand it? Well, at some point you give up and say, I'm going to figure out this when I get home, but then you never do because you're too lazy to think about it. And say, right? So if you look at the unscrupulous prover, you know, he has to fill all these tables with all these bits. And he knows what is this stupid verifier going to do? Well, it's going to, you know, pick a random edge, you know, we can model this, and then it's going to pick these inputs with this probability distribution. And then in fact, it's going to read these 3 bits and check their product. Okay. And we know that in the good case, you know, when this is a correct labeling of the corresponding graph, what will happen is he can satisfy exactly 1 minus delta fraction of these constraints. Okay. And by the soundness lemma that's still here, in fact, if, you know, you should remember the label covering, you know, you have to set parameters to make sure that there is no assignment in the label covering that does this, right? You want this to be smaller than the epsilon we had in the label cover thing. Which implies that no assignment will satisfy more than half the delta, as long as this is smaller than the epsilon you remember we had for the label cover.
The other side, right?
Pardon?
We'll find the labeling of delta.
Yeah, good. Yeah, sorry, yeah. Thank you. Right, so if you set the parameters this way, we know that there can't be an assignment that satisfies more than this delta prime fraction, and then we have the theorem. Yes?
Why did you have to switch to max 3 lin here? Why couldn't you have said all of this from max 3 sat?
Good. So, yeah, so that's the next thing. Well, why I could have actually. Yeah, you're saying
just because you're taking this product here.
Yeah. So what's in the end? What condition are we checking? You know, this. He's reading these 3 bits and checking the product. So it's a max 3 lin instance. So if he had read these 3 bits and instead took the OR of them, we would have had a max 3 sat instance.
Right.
And then we would have wanted to prove this thing with 7/8 instead of half, right?
Right.
Yeah. So we'll do that next time.
No, I guess I'm just wondering why did you go through why the digression to max 3 lin then?
Because when we're actually going to prove the soundness lemma is a lot easier to prove in this with.
Oh, okay.
It will be easier to prove the soundness lemma in this situation. But it's we're gonna do. Yeah, it's not clear from what I've said that we're in max 3 lin yet, but you'll see tomorrow. We're going to do max 3 sat.
Can I ask something? So
Sure.
Is this flipping of the sign of Zi with probability delta important for proving the soundness lemma itself?
Yes.
Okay. Right.
And we know it has to be, okay?
Okay, that's fine because otherwise you have perfect completeness. And
Yeah. Because otherwise, I mean, if it hadn't been needed, then we would have proven this theorem, right?
Yeah.
And that's a false theorem.
Yeah.
Because
I was just trying to figure out where it plays in because it's the part of the proof you haven't shown yet.
Yeah, no, this is, and you see that delta actually comes in explicitly here, right? So this will be 0 if we did have, and we'll see where it enters in the proof of the soundness lemma. But this is important, yeah. This is worth a chocolate. Yes, I have more questions or comments. There are no more chocolates, but you know, we can.
No chocolate.
We can. Okay, so then we continue tomorrow.